with the theory element of Lab 8, which for most of you is the important business. As said, all the theory is examinable in written assessment 2. What we do here, you'll be asked to do in written assessment 2. The VBA element is not as important. It's a bit of interest. It will be examinable though in the repeat assessment. Doing this lab should help you, in my opinion, for written assessment 2. Okay, so we've got some theory elements. There's supposed to be space for you here, space for you here, and unfortunately the space here is missing. But maybe we'll go into them regardless. I think I'm going to pause this and make these bigger. Okay, we're back. Right, so first of all, mesh the rod into 4 pieces. Now there is a little bit of help here that I suppose, yeah, there's some help that's if you're working on your own. So we've got a rod of length 4.8. Something like this. And this is all it's really asking for. So the temperature at x equal to 0 is 20. The temperature at x equal to 4.8 is 80. And notice that's fixed for all time. And the temperature is in the middle change in time. So I'm going to call this one temperature 1, this one temperature 2, and this one temperature 3. And note that we're talking, these are temperatures. Then down the bottom we have distance 0 along the beam, 4.8 divided into 4, this would be 1.2, 2.4, 3.6 in distance, and 4.8. So that's the meshing, that's important. Find the steady state. So in the steady state, what actually happens is that this goes to 0. The temperature doesn't change in time anymore. And as I said, yeah, that's what steady state is. And so you get that the second derivative with respect to distance goes to 0. And the curve with a second derivative of 0 is a straight line. So we have a straight line going from 20 to 80. So this is temperature, steady state really. Distance. And we're going from 20 x equals 0 to 80 at 4.5. So we're going from this point here up to this point here. Straight line looks like this. Now you could just kind of intuit that it goes up, you know, you've got 3 internal points. It's rising in a constant fashion. So do 80 minus 20 is 60. Divide that by 4, so it'll go up by 15 each time. You can do that, but also there'll be a question in the theory to basically write down the equation, this line. So we're talking y equal to mx plus c. So the temperature steady state, m is rise over run. So you've got a rise from 20 to 80, that's 60, over a run of 4.8 times x, and c is where it cuts, is 20. I might ask the calculator here for 60 divided by 4.8, 12.5. So we have 12.5x plus 20. So that's a different question that isn't asked here. And then the question is, what is the temperature at the grid point? So you can sub in 1.2, 2.4, 3.6 into this formula here, and you will end up with 35, 50, 65. 35, 50, 65, and that'll be used a little bit later on. Okay, and now for the 3 internal nodes, use finite differences to write the partial differential equation in the form the temperature at the next time as a function of the temperatures at the previous times. Now this has been done in a number of videos. Maybe I should just slow down here a little bit to do it again. If you know what's going on here, that's okay. You will be asked to do this in the written assessment too. Okay, So how we do this is now maybe we should write down the two finite difference things. So we'll be using that a first derivative at a point is approximated by the next value minus the previous value / current value divided by delta x. That'll be on your written assessment too. And a second derivative at a point is approximated by next minus twice plus 1 next minus twice current plus genuine previous. And it's divided by delta x squared. So we've got above a second derivative and a first derivative, and we will be approximating both of those using this, but it needs to be with respect to some grid. So the grid will go a little bit like this. So at a certain time, here's the rod. So this corresponds to T is equal to L. Actually, it's not necessarily the full rod, just a portion of the rod. I don't need all of it. So I just want to do a portion of the rod at a certain time. And this is at L time steps. And we're going to have the current temperature and its current in distance and time. Yeah, so this is what we're going, this is say, these are three, if we look up at our meshing, each one of the internal temperatures has a neighbor to the left and a neighbor to the right. So this is what we're representing here. So this is Ti, any of the internals. You've got a temperature to the right and a temperature to the left. And this is the x-axis. So these are changes in distance, given these. Okay. Now, you might say, well, there's time just above there, but actually T equal to L delta T is kind of signifying that this is at constant time. Those three temperatures there at the same time. And we label them with L, L, L. And now what we're going to do is put in the time axis, which goes up. And the time axis is, if I want to do something like that red thing over there, this vertical line is at a constant x. So x is I times delta x. So at some stage, the delta t and the delta x will have to be decided upon. So this here, it's if I go vertically, it's the same point on the rod, so the I doesn't change, but it is to the next time, L plus 1. So if I was to draw some more things here, up here, this corresponds to T is L plus 1 times the time step. And if I want to do similar here, this is x equal to I plus 1 times the distance step. And this is x equal to I minus 1 times the distance step. Okay, and what that means is we have this thing here is next with respect to time. In all cases, this is the current, whether you're going with respect to x or with respect to t. This one here is next with respect to distance. And this is previous with respect to distance. Okay, and what we're going to do, we'll just go up and grab the differential equation. 0.3 times the second partial derivative with respect to x is equal to the partial derivative with respect to time. And we're going to approximate both of these partial derivatives using the grid and the finite difference approximations up the top. So this implies approximately, so the second derivative with respect to distance. So if we look at it, we have this is next minus twice current plus previous, and that'll all be with respect to x. So this here being our current point. Next, the next one over is ti plus 1 minus twice the current ti plus the previous ti minus 1. And it is a partial derivative, so everything else is kept constant in particular time. So for all these, the time is the same. It's L delta t. And how we signify that is with an L, 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 divided by delta x squared. Now we actually do know delta x here because we've meshed our rod up. Delta x is the distance between these, 1.2. So we can, and here it says using delta t equal to 0.5. So we'll put that in as well. Right, and this is equal to, and now what we want to do is do the partial derivative with respect to time, approximate that using the thing in the top left. So the next temperature with respect to time, I would say, is TL plus 1 minus the current is TL, and not divided by delta x. It's t that it's changing, and so you get delta t. Now let me be clear, this is delta x, this is delta x, and then this is delta t, and it doesn't have to be a square or anything like that. Both of those, the partial derivative with respect to time is at constant distance, so both of these are at I. And then your job from here is to solve for this, and that's what this task is asking us. So what I would do is I'd multiply both sides by delta t. And I'm going to also write, if left is equal to right, right is equal to left. So multiplying the right hand side by delta t, I'm just going to have t I L plus 1 minus t I L equal to, now I'm multiplying the left hand side by delta t, so I'm going to have 0.3 times delta t, and I can pull out that delta x squared. And that's going to be my lambda times ti plus 1l minus twice til plus ti minus 1l. And then all I have to do is, well, I'll do two things. This is equal to lambda. And let's see what it actually is. 0.3 times the delta t was 0.5. The delta x to be squared is 1.2. It doesn't come, you get rounding error. So I'm going to put it in. I've got something here that if I put it in as decimals, it gives me decimals. So let me put them all in as fractions. 6 over 5. So 5 over 48. There's no point introducing rounding error here. Now the lambda, whenever, yeah, it's going to be 5 over 48. So all we have to do now, our job is to solve for this, is to add the current temperature I to both sides. And this is the theory element that you'll also be asked to do in written assessment too.